we're moving to the 2 times. Okay, t to t plus 1 and 2t plus 2. So 2 times here. So you need to have 2 times of growth. And then you add the corresponding seasonal component for that period. Let's say it is for March, for example, then you have to take the last estimate of the seasonal index for March. This one. Okay. So that's additive exponential, the whole is just additive. So S is the length of seasonality, the number of seasons. So example, S equal to 4 for quarterly data, S equal to 12 for monthly data, LT represents the level of the series, VT denotes the trend, ST is the seasonal component, FT plus N is the forecast for N period ahead. And so additive model, how to set the initial value. So to determine the initial estimate of the seasonal indices, we need to use at least one complete season data, that is the S period. Okay, so this one, remember this equation. So this is equation that we need to use to update whenever we have new information. But for the first one, we need to have initial value. So for L1, B1, S1, we need to set the first value. Okay, we need to have the initial value, the first one. How to set the first value? So as explained here for the level, unlike for linear or single exponential moving, L1 is just Y1. Remember? So this one different. For whole integers, we set as we start from the level number. Let's say you have quarterly data, so we can only start from L4. We cannot number L1, L2, L3. We cannot it manually Later on, if we use software like if we use NR, then we can get one because it used different way. So this one is just manual way. Let's say we determine it manually. This is the manual approach Yeah, the manual approach. So for to set the first level, it's not really the first one. The first one we can calculate is the level number equal to S. So meaning that the last observation in the first year. Okay, the first year. So we just the average of all observation in the first year and then divide by number of season. So you get the S. So not that this is a moving average of all the S, and so we'll eliminate the seasonality in the data. So if you look at the example, the given example in the Excel file, this one, for example 2. Okay, so we have the data, so it's monthly data. So we set the first, not really first, I mean initial value of the level. So we just take the average of the observation, the first 12 observation. Okay, so in the first year, okay, so just take average. So we get the LS, this one LS, and S is 12 equal to 12 because monthly data. For this example, if quarterly data, then you start number 4 L4. Okay, you take average of the first 4. And then to initialize trend, it is convenient to use 2 complete seasons. So you take, remember this one, the trend term represent what? It represents growth 1 period. So the B represents growth 1 period. So how to estimate growth 1 period? So what we can do, we take the difference between the same, if you have monthly data, the same month, between the 2 same month this year and last year, and then you divide number of season. For example, January this year, second year, minus January the first year, we divide by 12, you get one estimate of growth 1 period. Okay, this one. Let's say you have monthly data, so you take the difference between the value of the January second year minus January first year, divide by 12, you get one estimate of growth 1 period. Okay, and then you do the same for other month. For February, you get another estimate, one period, another estimate of growth, one period, and you do for March, and then until December. So in total, we have 12 estimate of growth for one period. So because we have 12, then you have to divide by 12 again. So that we get an estimate of growth for one period. Okay. So each of these give us one estimate of each of these. For January, one. For February, we have one estimate. For March, we have one estimate. And then we take sum of them. So basically, it is for 12 estimate. So you need to divide by 12 again. Okay. So that it gives you estimate of growth for one period. So that's how we set the first value of BS. So this one. So basically later on we will rely more on the software that he used and R. So this one just to give you understanding how if we were to do it manually, then how. But it's quite tedious to do that. Okay. So for example this one. So each of these terms is an estimate of trend or growth over one complete season, and the initial estimate of BS is taken as the average of the such term. And then for the seasonal indices are initialized by taking the difference between the first few data values to the mean of the first year. So seasonal, you just take the difference. Each of these value minus the LS. Each of these minus SS. So for example, for this one for January, and then for seasonal index for February, this value minus the LS. So each of these represent the initial estimate of seasonal index for January, February, and so on. But after that, we will update. Whenever we have new information, we update. Okay. And then this is your first estimate, the first initial value of level, the initial value of growth or trend, and then we have initial value for seasonal index. And then after that, you can start using this equation to update. So when we have the new second value of y, or the next value of y, then we can. So in this case, basically, when we have January next year, January for second year, then we start updating the level, the growth term as well as seasonal index. The smoothing parameter values are chosen to minimize SSE or MSE. As mentioned before, alpha, beta, and gamma, you actually can set any value that you feel suitable, alpha, beta, gamma. Okay, but normally this value we set to be small. I mean, especially for beta and gamma. But alpha, we can have a bigger, slightly bigger. But again, and alternatively, this value is not is not like parameter in other model that need to be estimated. But this one, we can assign any value that we feel suitable. Or alternatively, we can use optimization. So meaning that we find the optimal value of alpha, beta, and gamma that give us modest sum square of error. Okay. How to get the error? The error is just the difference between actual minus forecast. Actual minus forecast error. So sum square of error is just square of each of error and take sum of all error. Sum square of error. Okay. So as mentioned here, the smoothing parameter value are chosen to minimize SSE or MSE. Several other methods for initializing are also available. Okay, later on I will show you there's another way that perhaps used by R. That one. Okay, so this example I showed you just now. For example, this one. So let's say we set initial values and then we set our equation to update the level, equation to update the growth term or the trend term, and equation to update the seasonal index. And then let's say initially we set our alpha, beta, gamma to be 0.1. Let's say This is what we call a starting point. If we want to, when we perform optimization, so we need to put the starting point for the where the value. After that, when we run optimization, then the software will keep changing the values in order to find the smallest sum square of error. Our objective function is our objective function is sum square of error. It's just the sum square of all the errors. Okay, and error is just difference between actual minus forecast. Just forecast actual minus forecast gives error, and then you take sum square of error, then you get SSE sum square. So here we want to find once a set of values for alpha, beta, and gamma that give us the smallest SSE. So you can just use. It just gives you an idea how actually software perform optimization. But it's actually that it's better to. I mean, using other software, we are able to get the correct estimate. Excel sometimes also not. It's possible that Excel unable to find the smallest one. It just maybe find the second smallest one, but it believe in the smallest one. So it depends on the algorithm used by the software to perform the optimization. So okay, so this one, let's say we in order to perform optimization or to find the optimal value, we set all equal to 0.1 plus, and then we use solver, Excel solver, and then our objective function is one. Okay, maybe I reset all, and we do it again. So reset. So objective function, we want to minimize this one. Okay, objective function, we want to minimize by changing alpha, beta, and gamma. So by changing this. Okay, and then subject to the constraint that alpha, beta, and gamma to be between 0 and 1. Okay, so at this must be less than 1, and then again this must be greater than 0. Okay? So we have this constraint, and then just solve. Okay, and then we get answer. So alpha 0.84, beta 0.042, and gamma 1. Okay, that gives us the smallest value of SSE. So this is what we call as an optimal value of alpha, beta, and gamma that provide us the smallest value of SSE. Okay, so this data is forecasting new housing sales. You open the reviews file, housing sales, this one. Okay, so this is the same data. Why? Okay, and you open this one, you click this. If you just inspect the graph first, just inspect the graph, view graph. Okay, so this one, so it has this version, and it looks like it doesn't seem to be additive. Okay, so we choose to use additive seasonal version. So because it has seasonal version, then we can use whole winters additive. Okay. So you go to prop, exponential, simple, exponential smoothing. Okay, and then select whole winters additive. So it depends. If you want to assign your own value of alpha, beta, and gamma, then you put here. But if you use to provide you the optimal value, then you just put E like this. Just put E, so that it will estimate. Okay, it will provide you estimate of the alpha, beta, and gamma that will produce model SSE. smooth series forecast one step ahead for each sample and for multi-step ahead for our sample. So as mentioned here, forecast begin in period following estimation end point. Okay, this is sample. It's okay lah. Oh, it's active. So it gives you alpha, alpha, beta, gamma, and SSE as well. And then so beta 0, gamma 0 means what? It means that it will not update the trend, and it will not update the seasonal index. It just update the level. Okay, because the beta 0, gamma 0. So I don't prefer to use R, because R is I think it's compared. It has more possibility of selecting 0. And then this one represent what? Mean represent the last LT, the last updated level, the last updated trend BT, and then the last updated of seasonal index. Okay, this one seasonal, the last updated seasonal index. The last for the last year lah, for the last year. Okay. Okay, you go back to Excel file. You notice that after we update, and then in the end you produce forecast for our sample. Let's say this is the data up to this one, the data we have, and when we want to produce forecast for 1 step ahead, 2 step ahead, 3 step ahead, and so on, and then you can just use the formula given here. This one, the last updated level plus how many times how many step ahead forecast you need to multiply by growth one period, and then plus the corresponding season index. Okay, so for example this one for December, I saw December. So it is the last updated level plus 1 estimate of the growth one period, and then plus seasonal index for the previous, the last updated seasonal index for December. For December, because this is no forecast for December. Okay, so you cannot simply don't choose this one for November. You have to select the correct season index plus the corresponding season index. Okay, so that's the meaning of T minus S plus N. Okay, the T, the last is the sample size minus the seasonal number of frequency of seasonal variation, and how many step ahead and how many step ahead. Okay. So we do the same. This one for 2 step ahead. For 2 step ahead, the last updated level LT plus 2 times of BT. Okay, 2 times of growth for one period, because we are moving 2 step ahead from November to January, 2 step. So this one is the last LT plus 2 times BT, the last BT, and then the plus corresponding seasonal index for January, because this one forecast for January. Yeah. Okay, so that for the first year, this equation, this formula, this one T minus N plus 1 is only true for the first year. For the second year, you have to rotate lah. Okay, because if you just use this formula, it will select values outside sample, the empty cell here. So when it says for the second year, December, for the second year, forecast for the second year, it is the last updated level plus the last updated growth times how many step ahead, 13, and then you have to go back, use the last updated season index for December. Don't select this one. Don't select. The usual formula you drag, then you select this part. Okay. So this again, this formula T minus S plus 1 only true for the first year. For the second year, you have to rotate. You have to rotate. Go back to the first season index. The last season index for the first one. In this case, for example, December. Okay. So because for the case of this one, for example, if November, November selects one. If you simply drag the formula, you drag the formula down, it will select this one, which is not true, not correct. So you have to rotate. Okay. Rotate the estimate of the season index. So if you want to compute your forecast manually using this result, then you understand that. So how many steps here? And then you just LT, the last LT plus how many times BT, and then plus the corresponding this one. Okay. Corresponding season index. Alright, additive model. Sorry, additive we already discussed now. So now multiplicative. So multiplicative, it has the same number of equations, 4 equations. So but it has slightly different to the additive one. If you notice the second equation is exactly the same. Second equation is exactly the same like the one the additive has. Second equation, but the first one, the way we calculate seasonal adjusted value with the ratio. Remember for the multiplicative decomposition, to calculate seasonal adjusted value, you do not minus, you divide ratio. Okay, you divide. So you divide this is a seasonal adjusted value. We take ratio of y and the corresponding index. And then for this one, also the same, season index, the trend value, not minus, but ratio between y and the LT, the trend value, because this is multiplicative seasonal function. And then for forecast, the estimate of the level times the seasonal, the corresponding index, not plus, but the whole thing here times multiply the corresponding index. In terms of initial values, okay, so equation 2 is identical to equation 2 of the additive model. The only difference in the other equation are that season indices are now multiplied or divided instead of added or subtracted. The initial value of LS and BS are identical to those for the additive model. However, to initialize the indices we take ratio instead of minus. The additive y1 minus LS, but this one y1 divide over LS and then y2 over LS. So it is given by, okay, this one, how Winter's multiplicative. So this one is exactly the same. To set the initial value of LS and then BS also the same. But for the season index, we take ratio, we divide, not minus. Unlike additive, minus. So this minus this, next one, this divide over this, you can. And after that, you can update whenever we have new observation. After that, then we update using the equation. We update the level, and then we update the growth, we update the seasonal index. This one also the same like before. We can just perform just like for, if they say 0.1, 0.1, and then 0.1, then you can just perform optimization. Okay, so the optimal value that gives us model LSE alpha 0.8023, beta 0.0107, and gamma. So in this case, so this one, gamma equal to 1 means what? It means that we update seasonal, but we do not take into account the previous estimate. We just take totally, we totally use the new information, okay? Because gamma equal to 1. So in terms of forecast, it's the same. The forecast, how to use forecast just like before. but instead of plus we multiply. Instead of plus, multiply. Okay, if use align data, this one align data. So if you inspect graph, obviously is graph. So obviously it has multiplicative seasonal variation. So we have to use Pointers multiplicative. Okay, Pointers multiplicative. So you go to draw exponential pudding, simple exponential pudding, select Pointers multiplicative. So okay, so we have the estimate. If you compare the Excel just now, Excel we get 0.8, 0.011. We use the program the same, but it's not 0, 0, 0. Remember why we get different? Because if use different way to set initial value, initial value. We use different way because we do manual calculation in Excel. So there are many ways of setting the initial values. R also use different way. Enter you can see R produce different results. So you compare to the one produced by use. So your forecast, if you open YSM here, YSM. So our outsample period starting from January 1957. January 19. This one. So this one, the values before that, all the one step ahead forecast is FT plus 1 is sample, FT plus 1. But for our sample, it is FT plus 1 and then FT plus 2, FT plus 3, FT plus 4 and so on. Okay. So this one. And then they try to calculate. If they use the given result here and see, you calculate, let's say 12 step ahead, this one LT plus 12 times this plus 12 times this, and the whole thing times this one, seasonal index for number 12 for December. Okay. Try to calculate that one at home, see whether you get or not. If you don't get it, somewhere wrong, so you have to check. Meaning that you will not understand how to calculate, how the formula is used. Okay. So this one, okay, now we go to, okay, first. Okay, we use R. Now let's try to reproduce the result in R. That one, lecture 5. So you open exponential in R, the classical approach. This one. So we want to compare, we want to produce forecast using the classical version, the single exponential, collinear, Howitter's additive, Howitter's manipulative in R for the same data that we used before. So what you need to do, you open R Studio. Import data. Okay, so we need to import data which is given in this one, in the Excel file. So we have the same data as before for the single excluding inventory for whole linear, and then this one for whole winters additive, whole winters cumulative. So you import the data. So you go to File, Import Dataset, Excel. Browse, locate where you save the file. So this is lecture file. Okay. And just import. Okay, so we have the data here. So okay, because we want to use the data, we want to analyze the data inside this, what we call it, the data frame. Okay, and we need to use a test function first. The test function, and then we need to convert the data to be times data, and then okay, this one you just inspect the graph of the series. So you can type one by one, but I want to save time. I just copy and paste more than one sentences, and then just run it. You actually can do one by one. Okay. Okay, in order to estimate to get forecast for a single exponent moving, we can use SES function. SES that available in forecast package. So you have to call forecast package from library, and then you use SES function. You can just SES type the variable, the times data that we created now, and then it will provide the estimate of the smoothing parameters of smoothing constant using optimization by minimizing the subset of errors. And then you actually this one is already sufficient, but because I want to save because I want to save the result output, so I type like this now. So I save if I put like this, then it will save the output as an object. So whenever I type this, and then it will show the result, the estimate, the output. Okay, and then to see the values of estimate, you can use summary, yeah, and then plot to see the plot or the forecast for SES. Okay, so this one just the notes, because in R, if I put this symbol, it will ignore everything that we type after that. Okay, it will ignore because this one I want to waste time. I will copy and paste everything but in R we ignore this one because we put this symbol. Okay, if we put this symbol, then this one will not affect. Again, in R will ignore everything we type or we write after this. So so we need, because we want to do SES, we have to call it from forecast package for our library. Okay. So this is the forecast. The forecast produced. If you want to have any specific number of what step ahead forecast, you have to add H equal to 1. Okay. You understand this one? I think that one I already explained to you before, but we will perform estimation forecast. If you want to know the description of this, so it give you explanation this one. If you want to choose how many step ahead forecast it produce, this one the default is how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the default is 10. So if you want to produce the next 12 forecast, then you choose this one. You put comma H equal to 12. Okay. So this one. Alright. if you if you as simply like this, then it will estimate the initial value as well as the smoothing constant alpha. So initial value it will estimate as well. Optimization will find the values of initial value of the L1, not even L1. Basically, in R is L0. The initial value for level is as the value of a level at time 0. So it will be obtained through optimization. It will find the value of L0 that will give as well as alpha that is modest SSE. Okay. If you want to set any value of alpha, then you put at this line, you add alpha equal to what? Then you get the result. So this one just now, the estimate we get 0.0000001, and the initial value 202. Okay. And then if we set any value for alpha, let's say 0.5. So we get estimate alpha. I mean not estimate before we set the alpha to be 0.5, but estimate from the initial L1, not L0 initial state. It is 815. Alright, and then forecast given here. Forecast. So you can input this one like how to modify the command. So let's say you want different. You want to produce the next 24 observation and just put 24. And this is the level for the forecast interval, 80% forecast interval, 95% forecast interval, and then value of alpha, lambda, sure, okay. And then this one, if let's say you want to estimate initial value using heuristic scheme. Heuristic scheme, there is another way of heuristic scheme is that we simply simple means that we use a certain way of calculation, just like the one that we did before manually. That is considered as simple or heuristic scheme, not through optimization. In that you will not find optimal value of initial value of L0 or L1 and 0 for the level. But it just use certain way to calculate, and then it just find optimal value for the alpha. This is what we call as simple initial value for the level, just using simple way of calculation. Yeah. So just like what we did in Excel, the simple way of calculation. But it's not the same. It's not the same. But the way that we calculate in R calculate is not the same to what we use. But it had used the certain calculation. So you get use this one, alpha 0 initial estimate. It just take the first value of y. So initial value to 200. It just the first value of the series y1. Okay. Okay, hot linear. Hot linear use HOLT instead of SES, use HOLT. Okay. Okay. So to save time, you just I think copy and paste. This one for the inventory data, we use data for the first 24 observation. We need to remember you have to transform it to be time series data first. Otherwise, this function we do not know whether it is monthly or quarterly. What? Okay, you have to make it to be time series data first. So you put frequency 12, then you know it is monthly data. Frequency 12 monthly data. Okay. So we get forecast as well. So 80%, 95% forecast for the next for the next 10 months. So again, if you want to have the next 12 months, then you put a comma H equal 12, then you get the next 12 forecast for the next 12 months. This is called inter, so we consider there is no seasonal variation, but it has trend. This one, you want, for this example, if you want to set alpha and beta to this value, like before 0.2 and 0.05 and 0.2 per beta, then you need to put like this now. If this one is like what? This one is like alpha 0.3, beta 0.0001. Initial value for level and for BT, LT and initial value for BT. This one. So this one, if you want to set, we want to make the value fixed for alpha and beta, then you have to specify what value you want it to be, alpha what, beta what. Then okay, so this one, so we get 0.5, 0.2, and initial value of LT and BT. Hot winters, seasonal, using housing cell data. So we use HW, hot winters HW. But we need to specify whether it is additive or multiplicative seasonal variation. I mean, it is hot winters additive or hot winters multiplicative. You have to specify here seasonal, additive or multiplicative. So for the case of housing cell data, it is additive. Hot winters additive, we should use hot winters additive, then we have to use the data. Just like before, convert data to B type data first, and then you can use HW. And mention it is additive. Copy and paste everything. Okay, so produce forecast. I think this one it produce forecast longer. The default setting, the default rate, it produce forecast more than 10. But again, if you want to set the number of step ahead, then you just add like H equal to what. So this is your forecast, and then forecast interval, your alpha, optimal alpha 0.8, beta 0.01, gamma 0.0001, and the initial value of LT, BT, and ST. Seasoning text. For the case of airline data, for winters multiplicative, this one. So you have to mention a multiplicative. Series multiplicative. Okay, so just run it. So we get this. So the estimate of alpha, beta, and gamma given here. Initial value of LT, initial value of LT, BT, and ST. The forecast values. So you see that although we can get forecast in if use, so I mean R provide additional things. I mean each has its own advantage and disadvantage as compared to that. So it's good that you know to use both. That's why at least you use R. R is free software. Okay, before we have, let us do that session 4 first. the ETS will be discussed after break. ETS. Section 2, I think we have discussed, one. I just directly discussed section 3. Alright. So this one, but it's not that difficult for you to understand, right? So they given. This one, section 2, you just need to produce forecast based on the given estimates. This one, section 2. So you just use based on the printed equation. You just replace the value of t and then you get a forecast lah. Okay. And then question number 2 for section 2. It asks you this one how to use the result of cluster decomposition to produce forecast. This I already explained before during lecture. So just another example. So if you okay, now for this question, remember section 2, this one. Remember to produce forecast using the result decomposition is not necessarily using a linear model, linear trend model. The example that we used before during lecture, we used linear trend. We simply regress against time trend, but not necessarily. For this given example, we model the linear adjusted value, using trend, using the linear trend model and quadratic trend model, as well as this one not linear, right? This one exponential. Okay, and then we can select the one that has smaller value. Okay, so in this case we select exponential trend model, but it has smallest AIC and SIC, and then we use that to produce forecasts of the single adjusted values. After you get forecast adjusted value, and then you multiply with the single index. So how to get single index here? In the question, how to get single index? Because we know single adjusted value is calculated. How we calculate single adjusted? This is multiplicative or additive? Multiplication. So single adjusted is calculated by dividing YT over ST. Adjusted. So to get ST, you manipulate lah. Okay. So the one adjusted means that these plus values of the value of y is just yt over st. So to get st, it is yt over. Okay, so to get st, you just divide out. So yt, you have to think now. So this one of the question, one of the year before. So it requires you to think based on. I mean, you have to understand first, and then from what you understand, you have to figure out. So the seasonal index is not given here, but you can calculate because in this adjusted value is given. So yt divided by the adjusted value, you get the st. So from there you can calculate forecast. The forecast of seasonal adjusted values using exponential model and multiply seasonal index. So this one just to model the trend, the linear trend. So quadratic trend produces smallest. Number. This one you know how to estimate the model. I already you refer back to the previous note. Model the trend you just this one just model trend without system variation. So you just regress y, you just type y and then add expand. Sorry, not you just regress add trend plus 1. Okay. You know right? The one will be how you done before. Or you still want me to show how? So I just quickly show down. So just example. So remember before how to do it. So y regress again c. That's how we get the estimate. Okay. Our in sample up to 2010. So you get an estimate. Is it the same? 27. So for quadratic, you just add trend plus 1 square. Okay, exponential also refer better. I mean, you can just refer I think previously the English file that I provided before, the zip file, it has the command. Okay, you just do the same. Just click it. Okay. And then select this model because it has model AIC and SIC to produce forecast. And then you just produce forecast before. So you produce forecast, you just go to forecast. You specify, you put the name for forecast values, and then you specify the range of forecast, and then you should be able to get one. So SYF, you want to compute the forecast interval, you save it as E. Sample data until December 2010. So forecast the rate of forecast 2011 January up to 12 December. So you get forecast one. So 9 point MAPE 9.86. This is just the manual calculation. If you want to calculate the MAPE manually, then you need to have the Y forecast value, and then you can calculate the APE and MAPE. This is 95% forecast interval. So just now we have forecast value, and then we have SE. Forecast value here, our sample. So we calculate that. So forecast plus minus 1.96 times SE. So you get lower and upper forecast interval. So you get the same for the other models, for the tick as well as exponential. And we evaluate now. So in this case. So MAP we directly get from here, but for MSE you can just take square of the square of RMSE because RMSE is just the square root of the MSE. Okay, so you compare MSE for the quadratic trend model produce the most accurate forecast, but exponential trend model produce the worst forecast. But just remember the AIC and SIC do not necessarily suggest a model that use the most accurate our sample forecast, but it is for this case it is consistent to the AIC and SIC. I mean the performance of our sample it is consistent to the format and sample, but it's not necessarily will happen, always happen like that for all data. Relaxation 4. Alright, so that's section 4. The following are the designated indices calculated using the classical and decomposition, assuming the trend based on the decision adjusted value. Our data is given by this formula, and then prepare forecast for the next 12 months of year 6. So this also using the classical decomposition to produce forecast. I think I have already shared one example before during lecture. So this is another example Okay. So after we perform decomposition, we can analyze and then calculate synergistic values and then estimate forecast of the synergistic value, and then we can produce forecast for our sample, and then produce forecast for synergistic value and then forecast for the whiting cell. So this one additive, I think. This one additive. So instead of time multiply and then you plus. Okay, just like before, just like section 2, I think. Just now. Question number 2. Given below is the Canadian unemployment rate as a percentage of the civilian labor force from the first quarter 1974 to the quarter of 1975. So they estimate unemployment rate in the first quarter using this one just the moving average approach, and then using single exponential approach. So this one number 2 So this one moving average of 3, just take the last average of the last 3 observation, and then single exponential. Meaning we have to set initial value of L1. L1 is simply Y1, and then you this one is simply set the value of alpha 0.7. Okay. So you just use 0.7 because the question asked you to use 0.7. So and then produce forecast. So this one just one step in forecast. Okay. Number 3. So this one is for linear. Okay. Estimate level and trend component, and by setting alpha 0.5 beta 0.2, and complete one step in forecast for in sample data, and then calculate our sample forecast, calculate MAB. Okay, so just do like what we did before. So this one, so we have this one is quarterly data. So this one for linear. So we set initial value L1 to be Y1, and initial value for B1 equal to the first difference between the first 2 value of Y. Okay, and then after that you can update When we have B1, you update. Okay, using the given formula. So alpha 0.5 beta 0.2. Okay, and then after that you produce forecast. So forecast one step A forecast, 2 step A forecast. Remember the 2 times the last update level plus 2 times of the last updated growth. For 3 step A, 3 times. 4 step A, 4 times of the growth. And you can calculate the forecast error and forecast absolute percent error, and then you take average, you get an NAV. Okay. If we perform, if we use single exponential smoothing on the same data, so MAB we get 2.11. For this one, MAB is 0.412. So this one or as single exponential smoothing is better. Which one better? So this one single exponential smoothing, you use that one alpha 0.5, you get MDV 2.11. This one, linear 0.4, 1, 2. So this one better. Okay, this one better. Why is better? Because the series, the data has trend. Single exponent smoothing, it is not created to handle trend. It's just for the series that has horizontal without trend, without seasonal. But for linear allow us to take into account growth. You have DT. That's why so it perform better because the series has trend. The series itself has trend, keep increasing. Okay. So number 4, Howitter's additive and then complete forecast. So number 4, Howitter's additive. So this is semi-annual. So our LS is L2 lah. Okay, semi-annual data. So LS is L2. Okay, we just take average of these two, and then our initial value of growth. Okay, and then after that we use update. So this one initial value of the seasonal index. And then after that you update, and then you use forecast. So forecast for one step ahead. This one Howitter's additive. If manipulative, remember you have to multiply. Okay, it's additive. So just remember this part you have to. This one for first year is next one for the first semi-annual, second semi-annual, just you use this one. But then for the second year of forecast, you have to rotate and use this one because we don't have the index here, so you have to recycle this one, rotate. Okay. So for this one, you use this. Okay. And this one, you use this. So remember I mentioned just now, the ST plus ST minus S plus M is only true for the first year. The first year of the forecast here. Second year is no longer true. That's why you have to rotate and rotate. Okay, so I think we take half an hour break, and then after break we will do the ETS. I will introduce to you what is ETS, and then you have extra time. You can do your individual assignment. Okay, so we resume lecture at 7:50.